Module 7, this is on Introduction to Involute Gear Tooth Correction, and in this lecture I shall cover the Involute Spur Gear Tooth Correction part 1. This is Introduction to Gear Tooth Correction, Involute Gear Tooth Correction part 1, and the lecture will have concept of involute tooth. We will recapitulate how this involute tooth is generated, generation of involute tooth, basic rack and rack cutter, concept of gear tooth correction, why gear tooth correction is required, plus and minus correction, amount of correction, that is profile sheet. Now, this already we have seen how the involute teeth profile is generated, or we can say that instead of cross belt drive, we can use the involute tooth gear drive. We can replace the belt by involute tooth. What I have shown here, that one small drum and there is another a little bigger drum, which is connected by a belt. So, we can say that this is one drum and this is another drum, this is the belt, and let us consider initially it is rotating in these directions. Okay. Now, if we consider a point 1 which has come over here, which was initially, so this we may consider in this drum this point 1 which has come here from this point, and from 2 has come to this point while this drum is rotating. Actually, let us consider first that this point was here. So, while it is moving in this direction, this point is coming gradually here. So, if we take a locus of this point, next this locus of this point, next it has reached here. So, we are getting this profile. Okay. Now, if we consider the same way a point here, then if we rotate in the opposite directions, it will be here, then when it is coming over here, then like this, and gradually we will reach into this. So, this is another profile, right. Now, if we remove this belt and allow these two profile to drive the other, say suppose this is the driver and this is the driven, then while it is rotating like this from coming from this point to this point, this will be pushed as it was in the cross belt. So, this is the basic concept of the involute tooth profile. Now, to have the smooth gearing action, what we need, these profiles to be put on the drum at an equal interval, and again these profiles should not interfere with the other, should not foul with the other while it is rotating. Then only we will get the smooth motion as in case of cross belt drive. Now, these two drums are called basic drum. In case of involute gear teeth, this is important, this is the base circle on which the profile is generated. Physically, we cannot see on the gears which is the base circle, except the root circle and tip circle we may not have feeling there, but base circle will be there on which the profile is there. Okay. Now, if we consider a circle of infinite radius, then that will become a straight line. But as on the circle an involute can be generated, so what will be the involute profiles on the straight lines? That will be a basic rack. These are involute on, you can say, on the straight line. We have earlier I have discussed, then after considering the involute profile, if we would like to design a gears, we have give some proportion to the spacing of the profiles, both forward direction in the opposite directions. So, there will be a gap in between, and it is standardized that at a standard pitch circle that gap and that tooth thickness will be same. That can be used as a gears, gear and pinion. And then if we make that base circle is infinity, then we will get this rack. And as we see that this profile has been generated on a same line. So, alternatively we can say, if we take a blank and one of the gears, a pinion as a cutter, then it will definitely generate the other gear keeping the same center distance. Consider the previous one, these two drum. Now, small drum we have made with the teeth with a cutter, the other one we have kept a solid blank. Now, we are rotating and allowing to cut the teeth, then definitely it will be able to generate the other profile. Similarly, this rack cutter is also, if it is used as a cutter, that will be able to generate the gear. Now, here I have shown that the different dimensions of this rack cutter, but if this basic rack is used for transmitting the motion, in that case addendum will be one module, standard addendum will be one module. But in case if we are using that as a cutter, then this there will be extra material on the tip, which is the height of which is nothing but the clearance in the opposite side, clearance on the gear side. That means, for the cutter this addendum will be 1.25 for 20 degree standard teeth, because the addendum we take 1.25, we keep 0.25 clearance, whereas at the bottom it might be more, although it is, see it is written here, but it can be kept more, no harm. But here essentially this should be 0.25 of the module, and as there are sharp corners cannot give the better profile at the corner, slight corner radius is given. Okay. So, with this basic rack cutter we can generate the gear, as well as there are pinion cutter also. But as the generated gear, whether it is by the rack cutter or whether it is by the hub cutter or pinion cutter, basic equivalent gear on the plane of spur gear, direction of spur gears, straight tooth spur gear, this will be all will be same, only the motion will be different. If we use the pinion cutter, motion will be one type, if we use the rack cutter, motion will be other type. Anyway, this idea why I have given, because we will need that how using this cutter concept we can give the correction to the teeth. Here different proportion are given, which we can read. Also, say this is inner end of effective flank, and this is at the standard pitch line, it is called pitch line, not circle. This width of the teeth will be equal to width of the gap, and this is the circular pitch in case of gear. Here of course, it is the straight pitch, which nothing but P is equal to pi into m module, and if we consider this angle is the standard pressure angle. In this case, it is 20 degree. So, by drawing such an rack is not at all difficult, and not even manufacturing of such a rack is difficult. For that we do not need any gear cutting machines, we can generate with any machines, any milling machines, or which can generate this path profile. Now, first of all, although I have discussed what should be the minimum number of teeth, if we look into this figure, then where is the base circle? Now, there is the base circle, okay, on which the profile is generated, but root may be below the base circles. Actually, if we consider the root circle, this must be equal to, for straight tooth spur gear, z into module minus 2 into 1 point, sorry, radius means or root circle dia, Zm root dia is equal to z into module minus twice into 1.25 into module, okay, and base circle cos of pressure angle, in this case cos alpha. Now, if we equate, if we consider these two, at one point we can find, if we go on decreasing the teeth number, at one point we will find root dia will be less than base circle dia, but there is no harm as long as the no gearing action is coming below the base circle. Okay. So, this concept we should have in case of a standard pressure angle, say 20 degree, this number for which the base circle will come below the teeth number is above a critical number, which I have discussed earlier, but here again I shall discuss this issue. So, first of all we will consider what is the minimum critical number of teeth. Now, to find out that, what we shall consider, say let us consider this is the pitch line of a basic rack, but not the cutter, this is not the cutter, basic rack. So, if we allow this to meet with a gear, the point where it can mate, that is first mating, that might be the tangent of line of action with the base circle of the mating gear. So, now if we consider that say P q is the addendum factor into module, in case of standard we can consider this is just one module. So, we can write now P q is A f into module must be equal to R, here R is the pitch circle radius of this gear, mating gear, and minus R b, this one is the R b, this radius, into cos alpha minus this distance q to cell, this is O, okay, and this is R we have considered. Therefore, equating we get P q must be equal to R minus 1 minus cos square alpha minus R, that is equal to minus, sorry, that is equal to R sin square alpha. Now, this gives us a condition that addendum factor into module is equal to R sin square alpha, and R is equal to, now we consider that it is the minimum or critical number of teeth for which this tip of the basic rack is mating, first mating at the base circle, intersection of the base circle and the involute and the tangents of line of actions, that means this point. Okay. So, from there we can have that equate this, Z c can be written equal to 2 into A alpha divided by sin square alpha, and as the addendum factor standard addendum factor is 1, this can be as well written 2 by sin square alpha. If for alpha is equal to 20 degree, standard pressure angle 20 degree, this Z c becomes 17 point not something, it is slightly more than 17, slightly more than 17, and safely we can take the teeth number is equal to 17, minimum number of straight tooths per gear with 20 degree. Now, if it is less than that, in that case with addendum is equal to 1, this contact point will come below the base circle and which will not be involute, and definitely the conjugacy will not be maintained. Here is a question, can we take the teeth number less than the Z c for a system? Mind it that root might be below that base circle, because the root is non-acting portion of the gear, it is not taking active part. So, root can be given, say for example, when it is moving in this direction, as you see this has come much below the edge, this rack is moving in this direction. So, this will come up to this point. So, this root must be here, and so, but it will not affect the gearing action as it is below the base circle. Okay. Now, the question is that once we make it below this number, in case of 20 degree it is 17, below 17, in that case definitely this cutter will, this point will be below the base circle, and there will be non-conjugate actions as well as there will be a undercut like this. That means, then tooth will become like this. So, definitely we cannot use a tooth like this, neither we will get a conjugate action below this point. What can be done? One easy method of correcting the tooth is that we can shift the profile in the upward directions with the same cutter, and probably for which this root will become same like this, but then this effective portion of this one will not come below the base circle. So, that is the concept of gear tooth corrections, which we will see more in the next slides. Now, in this case, as I have already described, A is the addendum factor. Suppose if we take the addendum factor slightly less, in that case we will have the less number of teeth, but for the we will consider always on the standard one. Let us have a look into the more details about the tooth corrections. What we are doing now, we are considering that the cutter is having, this is instead of rack, it is having the cutter. Cutter means its addendum, its tip is equal to normal addendum of the gear teeth. So, therefore, we have considered AFC, AFC for standard it will be 1.25 into module, then our cutter is here. So, this is the cutter. Now, with this cutter, if we cut this say 17 teeth, we are cutting the 17 teeth with this cutter, with the rack cutter, then our teeth, the teeth will be something like this. Because we have used this tip, okay. This tip we have used and we have got the profile like this. It will work, it will be allowed, but when the teeth number is less, what we can do, we can, this was the initial pitch line, we can move the teeth in upward directions, that is say we have come over here and now we are generating the same with the same cutter, we are using this. Say earlier when the pitch line was here, with this cutter it could be at the bottom, much bottom, but now as it has been shaped, we will get still an effective profile which can be used for conjugate actions. Now, this similarly this cutter also can be, instead of withdrawing, it can be fed inside. Say for example, large gears, it is much more, teeth number is much more than 17 in case of 20 degree, then definitely we can make the tooth thin and tip will not till go under the base circle, or it will not generate the profile which is and which is not in conjugate action. So, this is the minus correction and this is called the plus correction. Plus correction means that we are withdrawing the rack cutter, that means with external teeth the center distance is increasing. If it is a pinion cutter, then the center distance between the pinion cutter and the rack cutter is increasing, sorry, the pinion and the pinion cutter it is increasing. So, we call plus correction, and if it is going inside, that is it is making the tooth thin, we call minus corrections. Now, why we need gear tooth correction? The tooth correction is primarily done to avoid undercut at the tooth root and dedendum region for gears with less than critical number of teeth. Say that means, if we in case of alpha is equal to 20 degree, if we take the teeth number less than 17. So, what we can do? We can give the plus correction, that means tooth we can make a thicker and we can avoid the undercut. So, this is basic purpose. It is also done to modify mating gears tooth shapes, so that they become more or less of equal strength. Usually in gear design, what we have seen that pinion for the same material, definitely pinion will be weaker, because it will have less amount of formative number of teeth. The magnitude of formative form factor, you can say form factor, magnitude of form factor will be less than gears. So, this means that pinion is weaker. Of course, by using different material we can make them of equal strength, but what we can do, even there is different material, still just to bring the stress level equal, we can modify the gears. So, that is another purpose which is done keeping in mind that gear set will have more life if it is not corrected. Modification of center distance mainly to make the center distance a good square value close to original CD of under uncorrected gears is another purpose. That means, we can give small corrections. Say for example, we have taken a gear set and module even the helical angle such that it is not multiple of 5, the center distance is not multiple of 5 or multiple of 10, and we would like to make it multiple of 5 and 10. Say center distance has become 103 millimeter, we would like to make it 100. Then possibly we can give negative correction to both pinion and gear, maybe more to the gear, less to pinion or only to gear to bring the center distance 100 millimeter, or else we can increase it by increase it up to 105 millimeter. In that case, probably we will strengthen the pinion teeth, we will give positive correction to the pinion. So, it is possible to make the center distance a square value, which is preferred usually, just introducing correction. It also helps in reduction in dynamics. If one teeth is weaker than other, in that case one will have more deflection than the other, and then when the load is released, it will have more motion than the other. So, dynamics will definitely be higher if they are of equal strength. So, this is another effect of the gear tooth corrections. Now, two types of gear tooth corrections are done in gear cutting. One is the addendum modification and other is tooth profile correction. First of all, addendum modification means that we increase or decrease the addendum as well as we shift the profile, and tooth profile corrections again we should consider the profile itself is slightly made non-involute and it is made in such a way after deformations it will become close to involute, but that is not possible because that will be load dependent, deflection will be load dependent. So, profile corrections is usually given to give the better life, and that is not an easy task. Normally, profile shifting and addendum truncation or adding to the addendum is the general way of correction. This is done simply by withdrawing the cutter or not allowing the cutter to cut into full depth or allowing the cutter to cut into more depth. So, that type of corrections are widely used, and next onwards we shall consider only the profile shifting, addendum modification and profile shifting. So, this part we have already discussed, and now addendum modification is that in gear technology such correction is termed as profile displacement or profile shift, which I have mentioned. In fact, by not allowing the cutter to reach its ideal feed limit or allowing it to higher depth than the ideal feed limit, such corrections are done. In gear technology, already I have mentioned this, the tooth height is selected accordingly. So, if necessary we can truncate the addendum or we can add the addendum. Geometrically keeping the base drum unaltered, parallel shift of the profile input profile is possible, and first case it is positive correction, that is positive addendum modification which results in greater tooth root width. obviously these increase strength in bending. In later case, root width reduces, resulting in lowering the bending strength. However, rate of such changes in strength with profile shift reduces with the increase in number of teeth. Such a correction is sometimes called as profile modifications, but in true sense there should not have any confusion. Profile correction is that we are altering the involute profile to some other profile to have the better gearing action. However, correction or modification in geometric shape of the profile is put into separate category, which is termed as tooth profile corrections, which I mentioned. In a mating gear pair, such a correction can be done without changing or with a minor change in center distance to make the center distance a round of figure, which is usually multiple of 5 millimeter in metric system. It is sometimes called as plus minus correction. Without calling is profile shift, we call plus minus corrections. Plus correction is given to the pinion and minus correction is given to the gear, that is usual, but as I told that to make the center distance lower, the minus correction can be given both, of course, looking into the strength of the teeth. With the change in root width, Lewis form factor of both pinion tooth and gear tooth are altered. Thus, selecting a suitable plus minus correction, we can reduce the difference in SD into Y. Here in this case, you can see this we can keep same for both gear and pinion, because in a stage they are transmitting the same load, contact load will be same, but here will be the difference, because due to the material this may be different. SD we have considered the allowable strength considering all factors, and Y is the form factor, that will definitely be less in case of pinion. Now, what we can do by modifying, keeping this material same, by modifying the tooth we can increase or decrease the Y, and then in such relations we can make the T by, because the torque in the other shaft is increasing, T by this part, T by Z into this part more or less same. So, this module will become exactly equal whether we design the gear or design the pinion. So, this is just to give an hint, but in spite of that in design it is not possible that we will make always the strength is equal, only we can decrease or increase, we can decrease the differences. In optimization, not the gear sizes, but also increases the life of the gear set. Now, there is it is mentioned as well that S correction and S0 correction, S correction plus minus, S0 correction plus minus. S plus minus correction means center distance will not be same, center distance will be varied, and plus minus correction plus, as I told that in external, in case of external gear the center distance will be more, the tooth will become thicker, and minus correction is the opposite, whereas it might be S0 plus minus correction, that means S0 means there is no change in center distance. And as you see in this figure, it is shown there is a plus correction is given, and the original profile which was this one has now become like this. after the correction, and then the cutter has been withdrawn by the amount of delta. So, plus correction in both external and tooth and gear means cutter offset with more CD, center distance is increasing, okay, and minus is opposite. Now, if we consider a correction factor x, then for plus minus corrections we can write delta is equal to plus minus into x into module. So, that means we have to mention what is the correction factor, plus x or minus x. Plus means the tooth thickness will be increased and minus means the tooth thickness will be decreased. So, ignore this value, it has no meaning. Okay. Where delta is the amount of profile shift or correction factor, m is the module and x is the profile shift or correction factor. Now, for this portion, although there is a I have mentioned about the reference books, but for this portion I have followed other books also Dean standard, but Moitro's book will be helpful. This will be available, this is available in Indian market and this is cheaper than any other available book on gear corrections. So, that is why I have mentioned this one. So, in this lecture we have basically learned what is the concept of gear tooth correction in straight tooth spur gear, and in the next lecture I shall give more details about the tooth corrections, their limitations, and by tooth corrections what are the changes and how to calculate tooth thickness, etc. Thank you.